Okay, let's jump right into a pretty cold reality. Whenever we picture emergency responses, we usually think of something super dynamic, right? Water deluge systems roaring to life, massive foam monitors spraying across a heli deck, emergency teams sprinting into action. Active fighting firing is absolutely essential. But what if those active systems fail? What if the firewater pumps just die? Or a fire is simply too massive to be put out immediately? Imagine for a second that all the pumps, all the hoses, and the alarms are just completely out of the equation. What is actually keeping the crew alive in those terrifying first few minutes?
To really understand the gravity of this, we have to frame just how hostile an offshore environment actually is. You are, for all intents and purposes, working on a metal island sitting right above churning ocean waters. Running away into an open field? Yeah, that's not an option here. Plus, you're entirely surrounded by highly pressurized, incredibly flammable fuel. Crude oil, natural gas, condensate. Toss in the abundant oxygen of the open atmosphere, and you have the absolute perfect recipe for a catastrophic hazard. When active systems fail out here, survival relies entirely on invisible, highly engineered systems that don't even need to be turned on. They protect the crew simply by being there.
In today's explainer, we're looking at the ultimate fight for time. The answer to that survival question lies in hidden static engineering that manipulates the single most critical resource in any emergency, and that is time. We call this passive fire protection. It requires zero power, no activation, and no operator intervention whatsoever. Its entire purpose is to absorb punishment, resist unimaginable heat, and delay structural failure just long enough to organize a safe evacuation.
Now, an offshore platform isn't just one giant open building. The entire safety design revolves around a concept called compartmentalization. Basically, the installation is intentionally sliced up into distinct, independent fire and blast zones. These zones are separated by heavily engineered fire-rated walls that we call bulkheads. The logic here is incredibly straightforward, but absolutely vital. If a fire breaks out in one process area, these bulkheads act like a cage. They trap the fire in that specific zone long enough for personnel to muster and for response teams to do their thing.
So in practice, what this means is that you are quite literally wrapping the most vulnerable spaces in thick defensive armor. You'll have these massively rated boundary walls, marked with ratings like A60 and H120, facing directly toward the high-risk process areas. These act as a protective shell around critical survival spaces, like your control room, the radio room, the stairwells. Then inside this fortified box, you'll find lesser-rated boundaries, like B15 or A0 partitions, for places like offices or the mess room. The platform is intentionally shielding its vital organs, so to speak.
But hey, a wall is only as strong as its weakest hole, right? An offshore platform is practically alive. It's full of electricity, fluids, and ventilation. Because of that, you have to punch holes in these massive fire bulkheads to run cables, pipes, and air ducts. But think about it. If a fire hits that wall, a tiny, simple gap around a pipe literally becomes a blowtorch shooting into the next room. That is why every single penetration, whether it's a pipe transit or a cable packing block, has to be rigorously engineered to meet the exact same fire rating as the bulkhead itself. There can be absolutely zero weak links.
Now, you might be wondering, just how tough do these walls actually need to be? Well, you're going to hear about two main types of fire divisions, A-class and H-class. Both are designed to prevent the passage of smoke and flame, and both restrict how hot the safe, unexposed side of the wall gets. But the conditions they are actually built to survive, completely different ballgame. And out offshore, that difference is literally a matter of life and death. Let's break it down. The A-class rating, like an A60 barrier, was originally developed for traditional ship fires. We're talking standard cellulosic fires. Think burning wood, paper, everyday furnishings. An A60 wall will limit the temperature rise on the safe side for at least 60 minutes. But a pressurized offshore hydrocarbon fire, that burns vastly hotter and much, much faster. That is exactly why the H-class, or hydrocarbon rating, is an absolute necessity for process-facing walls. An H120 rating means the barrier is fortified, usually with advanced mineral wool or ceramic fibers, to buy a full 120 minutes, 2 full hours of survival time against a raging oil or gas inferno.
But here's the thing. Walls aren't the only structures at risk. Let's talk about the very skeleton of the platform itself, the structural steel. 500 degrees Celsius. That is the terrifying temperature where unprotected structural steel rapidly begins losing its load-bearing strength. If it hits 600 degrees, it can completely fail and collapse. And in an unmitigated hydrocarbon fire, those steel beams can reach that critical failure temperature in just a matter of minutes. No way you can evacuate a rig in that time.
So how in the world do you protect bare metal from melting? You use passive fire protection coatings. There are two main approaches to creating this invisible shield directly on structural joints and I-beams: heavy, thick cementitious coatings and intumescent coating systems. Both of these have one simple job: insulate the vulnerable steel skeleton from the intense, structure-melting heat of a hydrocarbon fire.
Let's look at cementitious coatings first. This stuff acts as a literal physical jacket. It's a dense, heavy layer of specially formulated cement packed tightly around the steel profile. Honestly, it doesn't look very glamorous, but man, is it incredibly robust. It works just by putting a massive, non-combustible block of insulation between the naked steel and the roaring flames, which significantly slows down how fast heat transfers into the metal structure.
But perhaps even more fascinating are intumescent coatings. These are super clever. Under normal conditions, this material looks just like ordinary, smooth paint sitting on the steelwork. But when exposed to extreme heat, an incredibly cool chemical reaction is triggered. The coating dramatically expands and swells to many, many times its original thickness, transforming into a dense, thick char. This dramatic swelling bubbles up to create a highly effective insulating layer, physically buying the steel those precious minutes of strength it needs to keep the platform standing.
Okay, so all of these passive defenses, the compartmentalization, the H20 bulkheads, the intumescent paints, they all serve to protect one vital location above everything else, and that is the TSR, or Temporary Safe Refuge. This is the ultimate layer of the defensive onion. It's the designated sanctuary on the platform, usually located right within the accommodation block and muster stations. It's exactly where the crew retreats to safety while the emergency is assessed and an evacuation is formally organized. Think of the TSR as a highly engineered survival pod. It is entirely surrounded by those enhanced A60 and H20 boundaries we just talked about. But obviously, a fire also produces toxic smoke, right? So the TSR relies on independent HVAC systems and maintains what's called positive pressure. This means the air pressure inside the refuge is kept slightly higher than the air outside. If someone briefly opens a door, air rushes out, which physically prevents deadly smoke and gas from creeping in. Throw in emergency lighting, dedicated comms, survival food and water, and you basically have a self-sustaining lifeboat made of steel bolted right to the platform.
So we've talked extensively about fire, but we really need to pivot to the secondary, profoundly violent threat offshore: gas explosions. Because fires aren't the only hazard that requires a physical shield. If a flammable gas cloud leaks into a congested process area, an area full of dense pipes and equipment, and it finds a spark, it doesn't just burn, it detonates. This creates a massive blast wave, a sudden overpressure that can literally tear a platform apart in milliseconds. To combat this insane force, structural engineers use incredibly sophisticated computational fluid dynamics software, or CFD, to design heavy-duty blast walls. Unlike firewalls that are built to resist heat, blast walls act as massive shock absorbers. They are specifically rated to withstand defined overpressure loads, literally taking the physical punch of a gas explosion so the shockwave doesn't crush critical escape routes or the temporary safe refuge. They act as the final, unyielding physical bulwark against a catastrophic failure. When you step back and look at the whole picture, an offshore emergency is entirely a fight against the clock. It's all about buying time. At 1 minute, those intumescent coatings swell up to protect the steel framework. Through 60 minutes, A-class bulkheads block smoke and flame from spreading. And up to 120 minutes, heavy H-class boundaries and positive pressure systems allow the TSR to sustain human life, making sure every single worker has the time to muster, be accounted for, and board the lifeboats. Every single piece of passive engineering is fighting to buy the crew the time they need to get home.
It's honestly a profound reminder of the silent guardians built into these high-risk environments. These systems just sit quietly in the background day after day. They don't need alarms, they don't need flashing lights. They just wait for the day they are called upon to perform a literal miracle of chemistry and structural engineering. So it leaves us with a pretty interesting thought. Whether you are working on an offshore rig, sitting in a high-rise office building, or even just walking through an airport today, what invisible, passive engineering is quietly keeping you safe right now?